Hi, everyone. In today's lesson, we'll explore the importance of data analysis in viticulture. To guide our journey, we'll look at the role of data in viticulture and the key steps in the decision-making process driven by data. We'll then dive into the role of artificial intelligence, and in particular, machine learning and computer vision in viticulture, examining how they're applied to forecast yields, detect diseases, and assess grape maturity. We'll see how decision support systems help turn data into action. Finally, we'll discuss why ethical considerations matter when using AI in agriculture. We have more data than ever before. Soil sensors, drones scanning vineyards, satellite imagery, weather stations, soil analysis, and more provide us with a great amount of information. The key question is, what do we do with all this data? Without proper analysis, data is just noise. The real competitive advantage lies in transforming it into actionable insights too. Make strategic data-driven decisions. Optimize irrigation, fertilization, and disease management. Predict harvest yields with precision and reduce waste. Detect problems before they impact production. In modern viticulture, data is more than just numbers. It is the key to optimizing vineyard management, improving grape quality, and ensuring farm sustainability. Modern farming relies on quantitative data to ensure objective decision-making. The challenge is not just collecting data, but analyzing it effectively to enhance vineyard productivity and profitability. In this presentation, we'll explore how data analysis makes the difference between uncertainty and success in modern viticulture. Too much data, but only the data we interpret creates real value. In modern viticulture, making informed decisions is crucial for optimizing vineyard management, and precision viticulture plays a transformative role in this process. The decision-making process is a dynamic cycle that starts with vineyard monitoring and data collection, where advanced technologies record the vineyard's condition and a variety of factors affecting the vineyard, like soil conditions and weather patterns. These technologies provide real-time data to ensure precise monitoring of the vineyard. Once the data is collected, it's stored in a secure system where it can be accessed and analyzed. Data storage is crucial to ensure that historical data is available for comparison and trend analysis. The data is then processed through advanced transforming technologies that clean, organize, and analyze it, often through software that uses algorithms to extract meaningful insights. By identifying patterns and predicting future vineyard needs, this step transforms raw data into actionable information. Decision-making follows, where vineyard managers make informed choices based on the analyzed data. After decisions are made, it's time for the operational implementation, where strategies are put into action on the ground, supported by guidance technologies, which assist in the accurate execution of decisions. Finally, after the decisions are implemented, the cycle returns to data collection, where the results are monitored and new data is gathered, feeding back into the loop. Actions are monitored and the data is analyzed again, refining future decisions and improving vineyard management continuously. This iterative process, driven by data, is key to achieving sustainable and high-performing vineyards. Several tools enable data collection in vineyards, including proximal and remote sensing technologies that utilize different measurement methods. You can find more details in the VTskills lesson on remote and proximal sensing. With large amounts of data collected from different platforms and sensing technologies, the next step is making sense of it. How can we process and interpret such a vast amount of information? Traditional methods rely on human observation and manual analysis, which are time-consuming and limited in scale. However, automated approaches can help extract patterns and insights that would otherwise be difficult to detect. In this context, artificial intelligence, machine learning, deep learning, and computer vision can make a difference. These technologies enable the analysis of complex data sets, allowing for more efficient and objective decision-making in viticulture. Their application extends to key areas such as yield prediction, disease detection, and quality assessment, enabling the transformation of data into actionable knowledge. As a key driver of digital transformation, AI future applications are expected to bring significant changes. However, AI is already widely implemented in vineyards, wineries, and distribution processes. AI is transforming vineyard management by providing insights into key factors such as yield and grape characteristics. Machine intelligence, combined with sensor data and imagery, helps wine growers optimize crop care, adjusting treatments to improve yield, determine the best harvest time, and in this way ensure grape quality. In wineries, AI processes sensor data to optimize production. AI can predict wine quality by analyzing the composition of fermentation products, tracking maturation in barrels, and streamlining operations, ultimately saving time and costs. Also, wine marketers use AI to reach the end customer. AI is reshaping wine marketing by, for example, analyzing consumer preferences. An interesting application at the marketing level is virtual reality, which enhances wine tourism, allowing consumers to experience vineyards and wineries from home through immersive tastings. Additionally, the so-called AI-powered virtual sommeliers, by personalizing wine recommendations, are opening new market opportunities, attracting both investors and customers. Artificial intelligence is a field of computer science focused on developing intelligent systems capable of carrying out tasks that typically require human cognition. Much like the human brain, AI learns from experience by utilizing advanced algorithms and software to detect patterns and features within vast data sets. AI heavily relies on sensor technology to gather information, identify trends, and make predictions. Artificial intelligence is a broad field of knowledge. Machine learning is a part of AI, important, but not the only one. Machine learning enables computer systems to improve their performance on a specific task through experience, essentially allowing them to learn from data on their own without being explicitly programmed for each task. Neural networks are a technique used in machine learning. They're popular, but not the only option out there. Deep learning is one of the methods used to build, train, and apply neural networks. Deep learning networks have demonstrated significant advantages in extracting features from complex and nonlinear data. Computer vision is the process of analyzing images to extract data and obtain information. Computer vision techniques rely on machine learning and deep learning algorithms. Computer vision algorithms follow a structured framework consisting of multiple steps. One-dot pre-processing enhances image quality for subsequent tasks by applying techniques such as normalization, background removal, denoising, and feature extraction. Two-dot in the main task execution, the system generates raw outputs. This step can involve image classification, which means assigning a category to an entire image. Object detection, which allows for identifying and localizing objects within an image using bounding boxes. Segmentation, by classifying individual pixels, makes it possible to delineate object boundaries precisely. Three-dot post-dash processing refines and interprets the raw output for better accuracy and usability. Machine learning has three key components: algorithms, features, and data. Algorithms are the methods used to solve a problem. The algorithm works to optimize accuracy, performance, and the size of the model. It's through this process that the system learns and adapts. Features refer to the parameters or variables that are used to train the model. In the context of a dataset, these are usually the column names when the data is in table form. For example, in viticulture, features could include parameters like grape variety, soil moisture, temperature. Data plays a central role. For instance, when the goal is to detect diseases in vines, the system needs images of the diseases to learn from. The more diverse the dataset, the better. There are two primary ways to gather this data: manually or automatically. Machine learning is not a single approach, but a diverse field with multiple techniques, each designed to solve different types of problems. A key distinction is between supervised and unsupervised learning. Supervised learning uses labeled data to predict outcomes, with models like classification and regression, while unsupervised learning deals with unlabeled data and works by discovering patterns on its own, useful for tasks like clustering, for example, grouping vineyard zones, and pattern detection, for example, vine health monitoring. By mastering these techniques, we unlock new possibilities in viticulture. Supervised learning helps classify grape quality and predict yield. Unsupervised learning uncovers hidden patterns in vineyard data, among other possible applications. Classical learning focuses on simple, structured data with clearly defined features, making it efficient and easy to interpret. Unlike deep learning, which often acts as a black box, these methods allow winemakers, agronomists, and researchers to understand and justify their decisions. On the other hand, deep learning and neural networks, which mimic the way the human brain processes information, have proven highly effective in extracting features from complex nonlinear data. The term deep refers to the multiple interconnected layers within a neural network, which provide an advantage in processing complex inputs. This enables the automatic recognition of intricate patterns in large data sets, such as images. Deep learning includes convolutional neural networks, ideal for image recognition, and recurrent neural networks designed for sequential data like speech and text. Together, these techniques form the backbone of modern AI, from classical methods to advanced neural architectures, working together to solve problems of increasing complexity. Machine learning is revolutionizing how we process information, make predictions, and automate decision-making. As we continue to refine these techniques, their impact on industry, science, and daily life will only continue to grow. Machine learning is gaining rapid adoption in agriculture for predicting yield and quality, but its widespread implementation still faces challenges. These methods require specialized human expertise. Experts work iteratively to develop the most suitable machine learning pipeline. The complexity of agricultural environments demands complex algorithms, such as advanced knowledge in mathematics, coding, and model selection. The no free lunch theorem suggests that no single algorithm works best for every dataset, highlighting the need for tailored approaches. Even the most powerful algorithms may not work for all yield or grape quality prediction scenarios. When working on a machine learning project, following a structured workflow is essential to ensure accuracy and efficiency. This process typically involves several key steps. First, we begin with data cleaning and formatting, which is crucial since high-quality data leads to better models. Next, we conduct an exploratory data analysis to understand patterns and trends before moving on to feature selection, where we identify the most relevant variables. Once we have our data prepared, we compare the performance of multiple machine learning models to determine which one fits best. From there, we fine-tune the best model by adjusting its hyperparameters, ensuring optimal performance. The selected model is then evaluated on a test data set, and its results are interpreted to derive meaningful insights. Finally, we document our findings and conclusions to guide future work. Interestingly, as shown in the pie chart, a significant portion of the effort goes into cleaning and organizing data. This highlights a key insight. In machine learning, data preparation is the basis of success. This way, we ensure that the model is built on a solid data foundation, leading to more reliable and impactful results. Machine learning models cannot be directly applied to raw images because they do not take advantage of the spatial structure of images or the way pixels are connected. Additionally, images contain a vast number of variables, with each pixel representing a separate value. For instance, even a small 10x10 RGB image consists of approximately 300 variables. Image processing allows transforming raw images into usable data for machine learning models. For example, once the image of a plant in the vineyard is acquired, it is possible to convert it into a binary format, helping isolate the grape regions from the background, making them easier to analyze. Removing noise and irrelevant details through erosion processing enhances the clarity of the image and ensures more accurate results in subsequent steps. These pre-processing techniques prepare the image for contour extraction, which is essential for feature identification in the model, allowing, for example, for precise grape yield estimation. Data augmentation is often used in machine learning workflows to artificially increase the diversity of training images. This technique involves transforming the original images, for example, rotating, flipping, or adjusting brightness, to simulate different conditions, ultimately improving the robustness and accuracy of the model in real-world scenarios. To assess a model's ability to generalize to new data, machine learning methods must be tested on multiple datasets. This is typically done by splitting the dataset into a training set used to develop the model, a validation set, which is used to fine-tune parameters and assess performance during training, and an optional test set, an independent dataset that provides a more reliable evaluation of the model's real-world performance. Some online platforms offer free datasets that can be used for machine learning models, for example, for variety classification or wine quality prediction. Many of the datasets are image-based, useful for developing computer vision models for plant disease recognition, variety classification, and maturity estimation, among others. For example, the Surth Grape dataset is a comprehensive dataset specifically created to assess deep learning models for grape segmentation and maturity estimation. Images in the dataset are captured under diverse lighting conditions, viewing angles and occlusions, and annotated with masks and maturity levels. Accurately predicting vineyard yield is key to organizing the harvest, selecting high-quality grapes, balancing vegetative and reproductive growth, and broader to support wine growers' decisions. Traditional methods often struggle due to high interannual and spatial variability and inefficient or poor sampling techniques, relying on manual, labor-intensive methods that are time-consuming and often inaccurate. To improve this, crop simulation models and machine learning techniques have been developed, which offer promising alternatives to traditional vineyard yield forecasting by enhancing accuracy and efficiency. A major challenge is converting collected data into accurate yield estimations. The most common method involves automatically detecting individual grapes or clusters to determine their size or analyzing other vine structures. Additionally, 3D reconstruction techniques are used to improve yield estimation accuracy. Often, yield estimation is achieved by counting grapes, with the goal of converting the detected yield components into estimates of kg vine, kg ha, or HL ha. Automating this process is a central challenge in smart agriculture. In recent years, several techniques have been proposed. Computer vision and image processing are increasingly applied to yield estimation. Image processing techniques analyze images to extract yield-related variables like berry count, cluster size, leaf area, and the number of flowers, stems, and branches, and offer the advantage of quickly processing large volumes of data without the need for destructive field sampling. Deep learning algorithms have demonstrated solid capability in analyzing extensive historical data to recognize crop growth patterns and forecast future yields. The ability of deep learning methods to handle high-dimensional data and identify nonlinear relationships gives them an advantage over traditional approaches. Different deep learning models show varying performance in grape yield estimation. Convolutional neural networks, which excel in image processing, are widely used for object detection, enabling accurate identification of grape clusters despite occlusion by leaves or other vegetative elements. By enabling precise grape bunch recognition, deep learning techniques contribute to automated yield estimation and advancements in robotic harvesting, offering new solutions for precision viticulture. We have said that unlike manual sampling, computer vision automates data collection and analysis, reducing labor and improving efficiency. Images can be acquired using stationary cameras, mobile sensors, autonomous vehicles, UAVs, or even smartphones, enabling continuous monitoring and real-time updates with the possibility to be integrated with other agronomic tasks. The ability to autonomously scan entire vineyards allows for early-stage yield mapping, allowing targeted vineyard interventions and continuous updates until harvest. Classical image processing and machine learning techniques have been widely used in viticulture. However, they have some key limitations, including the need for careful selection of appropriate algorithms, as well as the requirement for partial environmental control, such as an artificial background or controlled lighting, since leaves, clusters, and environmental factors as wind and light conditions can obstruct measurements. Trellising, leaf removal, and cluster thinning affect data collection accuracy, requiring alignment between methodology and vineyard management. Moreover, most models are variety-dependent, making it difficult to develop a universal commercial solution for vineyards with multiple varieties. Models that estimate the number of flowers per inflorescence have the potential to be variety-independent. However, flower count alone could be insufficient for accurate yield estimation and should be combined with fruit set rate and/or average berry weight. Deep learning, on the other hand, appears to be more resilient to natural variations, but despite their potential, deep learning models face several challenges, including the need for large labeled datasets, model interpretability issues, and high computational costs, limiting practical applications. The labeling process is particularly time-consuming, which presents a major challenge. Plant diseases can lead to considerable yield losses and can affect the flavor of the final product. While traditional methods depend on expert evaluation, they can sometimes be subjective. Recent advancements in computing, especially deep learning, are revolutionizing disease identification, By offering efficient solutions, with numerous studies highlighting the success of convolutional neural networks in disease recognition. AI enhances pest management by analyzing complex data from different sources. Machine learning algorithms classify crop images, detect pest damage, and analyze sensor data to identify pest activity. Tools like drones equipped with cameras, IoT devices, and AI-powered traps provide real-time monitoring and early warnings, which, combined with predictive modeling, improve decision-making and targeted interventions. AI combines historical and real-time data, including weather patterns, crop cycles, and pest life stages, to forecast outbreaks, enabling proactive pest management. Additionally, AI-driven systems automate pest monitoring and identification, reducing labor needs and boosting productivity, for instance, through sensor-equipped robots that scan fields, collect data, and detect infestations. This approach aligns perfectly with the integrated pest management framework, enhancing eco-friendly practices. For more info, take a look at the VTskills topic on IPM. The upper figure illustrates the typical architecture of a region-based convolutional neural network used for a segmentation method for diseased vine leaves. This approach utilizes a selective search method to extract specific regions from images, focusing only on the most relevant areas. The lower figure shows the basic components of a grape leaf disease detection and classification study by applying deep learning methods such as CNNs and vision transformers. By fine-tuning 14 CNN and 17 VIT models, researchers achieved high accuracy, enhancing early disease detection and grape variety characterization. The process described in the study begins with data preparation, where images are carefully processed and split into training, testing, and validation sets. Then, instead of building models from scratch, which is a time-consuming and resource-intensive task, the study leverages transfer learning. This technique allows applying knowledge from previously trained models, significantly reducing computational complexity and the need for a large training dataset while maintaining accuracy. Transfer learning has become widely adopted because it enables efficient training on small datasets in a shorter time. Once trained, these models undergo rigorous testing and validation to ensure they can correctly classify diseases and are evaluated based on performance metrics. Another useful application for AI is the assessment of grape maturation, which involves a dynamic combination of biochemical, physiological, and physical transformations that take place throughout its growth and development. Assessing grape maturity allows for optimizing harvest timing and ensuring high-quality wine production. Advances in imaging technologies, particularly hyperspectral imaging and object detection, have introduced precise and non-destructive methods for evaluating grape ripeness and chemical composition. Object detection algorithms like YOLO, You Only Look Once, that quickly identifies and classifies objects in images, enable real-time identification and classification of single berries and different grape maturity stages, enables the monitoring of grape ripening as it progresses over time, even in white grape varieties, which can be difficult to distinguish from the surrounding foliage. The YOLO system divides an input image into a grid and predicts object classes and bounding box coordinates for each cell, making it highly efficient for detecting multiple objects in a single pass. The images used for maturity detection are captured during the ripening period, ensuring that different stages of grape development are recorded. Once acquired, they are labeled according to maturity levels, forming the basis for YOLO model training. An alternative approach to object detection using convolutional neural networks involves recognizing grape berries in images and then applying image segmentation to separate them from the background. Another promising method for grape maturity assessment uses hyperspectral imaging, which captures spectral data across a wide range of wavelengths, including the near-infrared spectrum. The chemical composition of wine grapes changes throughout the ripening process. Hyperspectral imaging has been employed to characterize these changes, capturing information beyond what traditional digital cameras can detect and without the need for destructive sampling. By developing spectral models trained with machine learning techniques, it is possible to predict the chemical information from imaging data, like total soluble solids and anthocyanin concentrations. Integrating hyperspectral imaging with agricultural machinery or robotic systems enables real-time, large-scale monitoring of grape composition across vineyard plots at different phenological stages, supporting efficient, spatially aware management of grape ripening. thus making selective harvesting more effective, improving resource efficiency, and ultimately improving wine quality. Similarly, the use of normalized difference vegetation index (NDVI) data from various sources, such as vehicle-mounted sensors, UAV imagery, and satellite data, provides additional insights into the vineyard's spatial variability. NDVI is known to correlate with factors like leaf area infestation and diseases, water status, anthocyanin content, tannins in the skin, yield forecast, and maturity properties. By leveraging NDVI in combination with machine learning models and using historical and ground data, it becomes possible to predict critical factors like degree Brix and pH, enhancing the ability to identify possible areas of early or late ripeness within a vineyard. The growing availability of free, high-periodicity satellite images makes this technology accessible even to smaller vineyards. However, some studies suggest that proximal sensing might offer more accurate estimates, as it is less affected by soil background and the lower resolution of satellite imagery. Though it may seem surprising that a machine can evaluate wine quality, taste is influenced by chemical properties affecting flavor, aroma, and overall perception. By analyzing wine's physicochemical composition, data sets can be created to extract insights through data science, helping identify what makes a wine taste good. Machine learning models can analyze these patterns to predict wine quality based on its chemical composition. While some studies have focused on predicting wine quality based on its final chemical composition, other research introduces a structured viticulture to wine quality pipeline approach, emphasizing that quality management begins in the vineyard and allowing for assessing wine quality from the earliest stages of production, incorporating viticultural data, grape juice composition, and wine analysis. By following this model, winemakers can anticipate wine characteristics at different stages of production, enabling better decision-making and quality control. Artificial intelligence is also changing how consumers select wine. An interesting application is the so-called virtual sommeliers, which recommend wines based on individual preferences, helping users to choose which wine to buy via smartphone apps. A decision support system transforms data into actionable agronomic advice through a graphical interface, which allows users to access insights and tailor recommendations to their specific needs. A decision support system needs to integrate key components to ensure practical usability. It includes automatic interpretation procedures that transform processed data into actionable agronomic advice and a graphical interface, which allows users to interact with the DSS. Interoperability is also crucial, enabling the DSS to integrate multiple monitoring and prediction systems, connecting with various data sources for more accurate and efficient decision-making. Here are some examples of decision support systems used in viticulture, designed for tasks such as fertilization, pruning, chemical treatments, and harvest management. Some systems focus on specific aspects, while others offer all-in-one solutions for comprehensive vineyard management. Many of these tools incorporate predictive models, leveraging data from sensors, weather forecasts, and historical trends to optimize decision-making and improve vineyard efficiency. AI in agriculture brings numerous advantages, but also raises ethical concerns that require proactive management. Issues such as farmer privacy, data ownership, and accountability for AI-related errors highlight the need for careful oversight. A study developed an ethical framework for the assessment of artificial intelligence-based solutions in agriculture that uses 6 principles: fairness, transparency, accountability, sustainability, privacy, and robustness. Agricultural technology providers play a crucial role in ensuring the ethical and sustainable use of agricultural data and technologies. Clear licensing agreements should inform farmers about data collection, usage, and sharing. Training, user testing, and cybersecurity protocols are essential. Predictive AI can anticipate equipment failures and improve asset management. Adopting global standards such as IEEE ethics, ISO AI standards, and EU guidelines and policies such as the European AI Strategy, Data Act, Data Governance Act, and the EU Code of Conduct on Agricultural Data Sharing by Contractual Agreement for trustworthy AI will further ensure fairness, transparency, and reliability in agricultural technology. To improve this approach, various initiatives have taken place. Agri-Food TF, part of the EU's Digital Europe program, supports the development of trustworthy AI by helping companies test and validate AI and robotic solutions tailored to the agri-food sector. It offers a wide range of services, from technical testing to ethical and legal assessments, ensuring responsible innovation. Another example is Agdata a French data sharing platform that connects public and private stakeholders to drive the digital transformation of agriculture. It promotes transparency, data sovereignty, and collaboration, ensuring that farmers retain control over their data while benefiting from AI-driven solutions. Before we conclude, here are the references used throughout this presentation. These sources provide further insights into the topics we discussed.